You will never forget the maximum principle again. I didn't truly get it before my PhD, but the logic behind it is a pure childhood math. First, let's clarify. I'm talking about the maximum principle for the Laplace's equation. Let u be a harmonic function in the domain omega. This is how we call a function with zero Laplacian. Then it can attain its minimum and maximum values only on the boundary unless it is just a constant. A simple school inequality for the arithmetic mean helps to explain this. It says that the average of four numbers cannot be greater than their maximum and less than their minimum. But how is this connected to PDE? Very simply, we can discretize. Imagine that our domain omega is two-dimensional, and let us place a fine grid on it with the mesh size delta x. Then, the second derivative in x can be approximated by the finite differences on the grid. The same holds for the derivative in y. Then the approximation of the Laplacian is equal to the sum of the values at the adjacent points minus 4 u of x divided by delta x squared. Delta u equal to 0 implies that the value in the middle is equal to the arithmetic mean of the values around it. So at least one of the values at the points x1, x2, x3, x4 is not greater than u of x, and at least one is not smaller. We repeat exactly the same argument for the next grid points and keep moving further and further. In the end, we get that minimum and maximum can only be attained in the boundary grid points. And that is exactly the maximum principle, but deduced from the simple arithmetic average inequality. My name is Lev, I'm a PhD student in mathematics. Follow if you want to know more.